Uh, so thank you so much, and in particular, Dave, thank you so much for having me over. I've been looking forward to this so much. And my name's Muriel, and I'm going to talk about randomly network coding and perspectives in general on algebraic coding in P2P networks. And you'll see towards the end why we're particularly going to look at some other types of coding that people look at doing in propagation. So I'll just start a little bit. I'm Muriel. I'm on leave from MIT as a co-founder of Optimum, and actually my co-founder Kent is back there. Things were going great at MIT, and I was getting all the little awards that people like when you're in academia. And one of my friends told me, Shiram Vishwanath was one of the advisors, Muriel, the stuff you've been doing really, really is needed right now in Web3. And so I jumped. And here I am in front of you. I jumped from my comfy office with the coffee machine and the great whiteboard and so on. So I've been working on network coding pretty much my entire career. I lead the network coding relevant communications group at MIT. By trade, I'm an information theorist, if that can be called a trade. Let's call it by background. And so, coding, the optimal behavior of how you manage data, how you manage information, that's basically my bread and butter. So it was really so exciting to be able to take this technology that we'd been working on for so long in the lab and to bring it. And also to realize that people cared, that we have this amazing set of backers. We announced not that long ago our seed round, and that people are really excited about the tech and they want to hear about it, and they realize the potential. So why did Shriram tell me, Muriel, this is really needed in Web3? Well, to me, the thing that makes Web3 interesting, and I think this is going to resonate particularly, around the Ethereum community, is the fact that you can make a decentralized computer. And you can have somewhat different views of what a computer is, but by and large, a computer, since von Neumann, right after World War II, is roughly this. You ask it to do something, it spits out an answer, and in the middle, it does computation. And then the computation also relies on having access to data. So you have data, and then you have a bus, which is basically interfacing between the computation and the data. And a lot of what we think of computation is actually also the read-writing of data for intermediate steps. Okay. And this is basically, if you will, your GPU, CPU. This is roughly your operating system with all the applications on top of it. So, fairly recognizable in Web3 world relative to what von Neumann had in mind. And so I'm going to put, and of course, people put sometimes some extra layers, but we can at least agree on these layers, that those layers are somewhat recognizable, whatever systems class or you took, as undergrad, if you took one, the stuff here looks pretty recognizable. It's really cleverly done, but at least you're not like, what is that, And the part down here looks pretty different. And in particular, what I'm going to want to talk about today is this gossip aspect, where, the gossip is this decentralized bus. It's a decentralized propagation of the data to and from computation, memory, and back and forth, and writing to the ledger, reading from the ledger, or reading whether something's available from the ledger, which is what DA is. It's just a proto-read, effectively. And then, all of these exchanges that are happening of data in a decentralized fashion, what all of you basically are working on. So we're going to really talk about this data propagation. We also work at Optimum on other parts of the memory. Let's call it the ROM, the read-only memory, which is basically the ledger. You write to it, but you don't modify it. And then the RAM, which is basically the state machine. And we use coding for all of this, but it's really the first part that I'm looking forward to discussing with you today. So basically, the idea here is we're going to have this, optimum P2P as the networking part in this abstraction of the world computer. Okay, so that's kind of just the background. What you probably are more interested in doing, I'm hoping, today is for us to discuss a little bit. No, it's okay. I can use my, no, you guys hear me? No, I need to use, oh, okay. Yeah, thanks. All right. What we do is we use coding, algebraic coding. And basically, the idea behind coding is, data is not like, it's not like sending crates of apples. They're numbers. And one of the great things you can do with numbers is you can make equations out of these numbers and represent the same information in different ways, right? So that's what information tells you about, is different ways of representing information so that you achieve some particular goal that you're trying to get to. And so if you look at different pieces, as here piece 1 through piece 5, what we're going to do is we're going to be making algebraic mixtures from pieces. And if you have an algebraic mixture, really what it means is that you have a matrix that you've created. And if I have 5 unknowns and you have, 5 equations, unless those equations are not independent, you should be able to recover the same 5 unknowns. Okay, that's very simple. Now, how hard is that to then create those equations? So one of the things you could do is you could be very careful in your selecting of the coefficients in the equations, so that you're for sure going to get 5 equations that are linearly independent, right? And we would all know how to do that. The other approach is the following. I go, okay, really what I have is I have x1 through x5, my 5 unknowns. I'm going to have a matrix with coefficients, alpha 1, 1, alpha 1, 2, alpha 2, 1, blah, 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 right? And I just want this matrix to be invertible. That's it, right? So that's all I need. I need the matrix to be invertible so that whatever is the output of this is something that I can get back the original x. Okay, how do we check if a matrix is invertible? Yay, good. All right, we check the determinant. Okay, so here's my m. And the question is, is my determinant 0 or not? Right? If it's not 0, then I can invert it. Okay, that's good. So for the determinant is a multinomial in these alphas, right? That's what the determinant is going to be. And imagine that I gave you a homework problem where instead of asking you to find a solution, say make this equal to 0, I ask you to find a non-solution, right? Now, you could try to solve the solution and then take a different number. But really what you would do is to say, well, I'm just going to take a number at random and stick it in there, because chances are it's not going to be a solution, right? Most things are not solutions. That's why solutions are hard to find. So really what we're trying to do is we're trying to make sure the determinant is non-zero. So I'm going to take these alphas randomly. Now you have to be a little careful, because we're working in a finite field, right? We're not working in the reals with some floating point nightmare, okay? We're working in a finite field. Now, if your finite field is 2, like binary, you've got a problem. Why? Because if you have a simple, a simple polynomial like alpha squared minus alpha, well, this is a non-zero polynomial. It can take values, right? I mean, if alpha is 3, this is not 0, okay? But if I only have 2 values, 0 and 1, that's always going to be 0, right? Because So that's no good. So I can take it randomly as long as I have enough choices in how I pick randomly. Does that make sense? Right? And I'm going to talk as though I was working in a prime field. Okay, so prime fields, binary, everybody's, favorite prime field. Days of the week, modulo 7, everybody's second favorite prime field. I don't know what your other favorite prime field are. Some of your GPUs use Z31, for FFT. So, there's prime fields around there. There's basically what we call Galois fields, écarts de Galois in French, right? And basically, this is what we're working on. We don't actually work in prime fields. We actually, when we implement it, we work in extensions of binary, because then everything's as easy to do as if you were in binary, and you still get the size of the field, right? You're just trying to get a field large enough that if you pick something at random, you're not likely to hit a root of the determinant. That's it. Everybody happy? Okay, so I'm going to call it Q, but think that it's actually generally we work not in a F sub Q, but we generally work in an F sub 2 to the M. Okay, and the M doesn't have to be very large, and roughly, basically, the probability something goes wrong is this is going with the size of the field. So, if my field was only of size 2, then the probability of something going wrong is a half. No good, right? If my field is, 2 to the 8 is 1 over 2 to the 8, 1 over 2 to the 16, things are fine. Okay, so equations here in this M are going to be linearly independent with probability that's roughly 1 over 1 minus Q. You can make this a little bit tighter, but who cares, right? So that's roughly what it gives. So one of the things that's very interesting here is the following. When I take these coefficients randomly, if I take two equations, say the result of, applying just like 2 columns here. When I take this randomly, and I combine 2 equations, I get another random equation, right? So if you say, basically, I'm only taking some subset of the output here of this multiplication, and I combine some of these, it's also a random equation. Does that make sense? If I had a very strict structure, and we'll look later at codes that have a strict structure here, then basically, if I have a strict structure, I can't just randomly combine things and have a strict structure. It's like keeping your house really messy. You can keep your house really messy by just keeping it messy and doing random things. Keeping it neat is really hard. Okay, I mean, I'm not suggesting you keep your house messy, but just saying, that's basically the same thing here. Okay. I just want to point out before I go into this, because I'm going to geek out with you guys, because I figured that's your vibe, and if it's not, I'm really sorry. But we are actually working right now with a lot of wonderful operators on private testnet. So and I'll show you results later, but before I go into the math, it's like, this is real, okay? Well, actually, they're not reals. They're in a finite field, but the tech is real. All right. Okay, very good. Okay, so I'm gonna just step back and think of gossip in sort of the high level the high level setting. Okay, so gossip, you have a group of people, somebody has a message, and you are going to basically be getting a source here that's going to send to somebody, say at time 1, and then some at time 2, maybe this source tells it to somebody else, and this person tells it to somebody, and et cetera, et cetera, et cetera. Okay, basically gossip. That's we agree that that's basically the high level abstraction that we're thinking of right here. Okay, so I'm going to take something where each node can potentially talk to just one node at a time. You can change this. It doesn't really change the analysis. I'm going to look at something where you have discrete time rounds. It's just so that it's easier for analysis. Obviously, the things are synchronous, okay? Nodes only have local information, right? So it's not like this node here knows that the other node over there doesn't have X, Y, or Z, okay? You only just know basically your neighbors. And the node is a communication partner in this case. So push is push, as you guys all know. You decide who you talk to. Pull typically is a little faster. A called node transmits to a caller node. Basically, you go, hey, look, can you give me something? Okay? But it turns out that when you look in an order, and I'm going to be doing an order analysis, this is, it doesn't really matter if you do push or pull. Okay, so basically, what's the known result out there? That if I have this one message, okay, and I want to disseminate to everybody, it's going to go with n people as order log n with high probability. Right? You basically create a tree. That's basically what's happening. Okay? You're creating a tree to disseminate. And so the very coarse analysis, if instead of having one message, you have k messages, that it's going to take you order k log n, right? You do one message, then you do the next, and so on. All right. Now, obviously, since I'm transmitting one message at a time, the best that I could do is order k, right? I mean, and then basically that does not get slower this with n. So basically the problem that we have here is as n gets larger, obviously this gets slower, right? That's how it's scaling. And the best that I could do is to have, and I'm not going to be able to not get it slower with k, right? Because the more I have to send, well, the more rounds it's going to take me, right? But the best I could do, the best I could ever hope for is order k. Like if I could just perfectly pipeline the thing, that's the best I could hope to do, right? So we're going to see whether we can get to actually basically being scale-free, basically not caring about n. Yes, we can. All right, how can we do that? All right, so remember, I'm gossiping these k messages. And let's go a little bit into why things get hairy when you go to these k messages. All right. This is the coupon collector problem. So we saw the duplicates earlier. And that's basically the coupon collector problem. So the coupon collector problem is the problem we're all familiar with if we've ever made any sort of collection of anything. You start collecting. I can remember my kids were collecting Pokemon cards, and at the beginning it was really exciting because every time they got a new Pokemon card, it was a Pokemon card they didn't have, And then they get more and more Pokemon cards, and then once you get half the Pokemon cards, and half of the time you run into a Pokemon card, it's something you already have. Right? By the time you have 90% of them, not that they ever got there, but 90% of the time that you meet a Pokemon card is something you already have. So basically what happens is it's easy to get started on a collection, but the duplicates, as you have more and more stuff, you're more and more likely to get a duplicate. Does that make sense? Right? So that's what's called the coupon collector problem. You may have seen it that way. Again, depending on your undergrad background, but, whatever you've seen, we've all had that experience that at the beginning, building up the collection seems easy, and at the end, it seems hard because it is, right? That's basically what's happening. All right. So I'm going to do a high-level analysis of where we're going to be using the random linear network coding that I, waved my hands to explain, all right? And we're going to see how I can get to this order k, all right? So this is the magic trick. All right, here's the magic trick. So suppose that the k messages are sort of uniformly spread out in my network of n nodes to start out with, right? That's my assumption. And here I am, I'm node u. And I'm waiting to get a equation which is going to increase the size of the degrees of freedom of the independent equations in the matrix that I see. So what am I doing when I'm a node in this coding system? I first get one row of M, then I get the other row of M, right? I'm gathering equations. And the overhead of these coefficients is very, very small because, you know, if I'm working over bytes and I'm sending you, you know, kilobytes, then it's like 1 in 1,000, right? Basically. Okay. So here I am. I'm gathering M's and I'm trying to see if my, you know, when the degree of my M is going up. Does that make sense? So here I am, I'm node U, and I'm going to take, you know, again, this is for ease of analysis. I'm going to take a node U that doesn't even get out of bed unless at least half the nodes that are out there can be helpful. And helpful means that they have the subspace that is generated by their M's, by their local space, okay, is not a subspace that they already have. That is to say that somebody is helpful to me if they know something that I don't know. Otherwise, they're not helpful to me. Otherwise, they're a repeat. Does it make sense? Okay? So I'm node U here, and I refuse to get out of bed for anything less than half of the nodes being helpful to me. Only because I'm like, oh, most of them are not helpful to me. You know, call me back when you know, I'm pretty likely to get something that's helpful to me. Okay. So F is going to be the fraction of helpful nodes, and S is just basically a fraction of helpful nodes. It's 1 minus F. So as I said, I'm assuming a worst case scenario where node U, rather than engaging in gossip, you know, in an active and helpful way all the time, is actually refusing to get out of bed. Now, I'm going to go in these different phases, okay, where I is actually the dimension, so the number of basically independent rows of the matrix M that U has right now. Make sense? So maybe I needed 5 things, and right now I am at 3. Make sense? Everybody happy? All right, great. So at the beginning of the phase, roughly the fraction of nodes that are helpful is going to be k minus I over k, right? So for instance, if already I is k over 2, right, then this means that F is already k over 2, right? If I is, you know, 9/10 of k, all right, then that means that F is 1/10. So when 90% of the people basically know stuff I already know, only 10% of the people are helpful, okay? And I basically don't do anything until that gets to be 50% of the people. Does that make sense? Not that I'm suggesting you run it this way. This is just to make it super easy to analyze. How many people are happy? A lot of people are happy. Great, super. Okay. So does it make sense? So I'm sitting there until I go, well, you know, wake me up when most, you know, at least half of the people are going to be helpful to me. Okay. So there's going to be a first phase where I'm going to just watch as unhelpful nodes transform into helpful nodes. Okay? And any unhelpful node that's called by a helpful node is going to increase its degree with probably 1 over 1 minus q. Basically with probably roughly 1, right? The q is the fudge factor for the field size. All right. So the number of unhelpful nodes that are pushed by helpful nodes is roughly NF. Makes sense? At any time, right? So roughly NF. F was a fraction. There were n nodes. Does it make sense? So I'm sitting here as you watching, you know, there's NF nodes here, 1 minus F n nodes here, and, you know, they're getting pushed. Okay. So the unhelpful nodes that become helpful nodes after one round is roughly NF, fudge factor. So from one round, I go from having F to having F, because the helpful nodes stay helpful, plus F1 minus Q for, remember, this is the fraction, because I had NF plus, I have NF plus NF1 minus 1 over Q. Does that make sense? So the fraction is, yeah? Okay. All right. So I started with F being roughly K minus I over K. So now my F, after one round, you know, has increased by roughly a factor of 2. And at each round, roughly by this factor of 2 minus the fudge factor from the field size. Okay? So after R rounds, I just put an R here. Basically, like each time I just double. Right? That's basically what's happening. Each time I just double the fraction of helpful nodes. Yeah. Okay. So, you know, basically after, you know, forget about this log 2, whatever. Basically after roughly log K over K minus I, Ri rounds, I get to F being 2, being 1/2. So I basically just take the log here, right? I want my F to be 1/2. So how many times do I need to turn the crank to get to my F being 1/2, given that my F roughly doubles each time? Good? Yeah. All right. At this point, is everybody happy? If you're not happy, tell me. I mean, you know, like about this, your life, you know, you're on your own. Okay. All right. Okay, so now F got to be 1/2, and node U wakes up again. It's like, okay, it's worth a shot now getting involved. And what does node U do? Node U goes, okay, great. I'm going to listen now because, you know, I have a probably at least 1/2 that a node is going to be helpful to me, right? Because that's a fraction of helpful nodes. Now, what's the probability that a helpful node increases dimension of U? So I need to have a particular node has, you know, 1 over n probability of being the one that connects. I have the fudge factor of 1 over Q. So, and I have that half of the nodes are helpful. Okay, so the only way the dimension is not going to be helpful is if, remember, the probability that a helpful node increases is, a particular helpful node increases is that 1 over n, roughly. So it's the probability that it doesn't increase, which is 1 minus the probability it does increase, so 1 minus the probability it increases. Okay? And then there's n over 2, so every n over 2 node has to fail to help me for things not to go, not to increase. Right? It has to be that all of those nodes fail to help me. Pardon? Oh, it's not a half. This is for my. This is just to make my life easier in analyzing. Okay. So let me emphasize. Node U doesn't actually sit around doing nothing. This is even if node U was to decide to sit around and do nothing, I would still get to order K. I can only do better because obviously node U isn't sitting around doing nothing. Node U is actually sitting around, you know, being interested. Okay? I could have picked a third. I could have picked whatever, right? It's just the easiest thing. But actually, this is very much a worst case thing. Does that make sense? It's worst case. It's just for analysis. So let me repeat that. Node U does not actually sit around doing nothing in reality. This is for ease of analysis. I'm pretending that it doesn't, and I go, even if node U was a complete slacker, I can still get to order K. Right? But I can only do better in reality because node U is not sitting around doing nothing. Make sense? So it's a bound. And then if I show you that the boundary is order k, and I know I can't do better than order k, done. Okay, and then you get to have coffee after a little bit. Yes?
Yeah, I just wanted to ask about this first case, because you have the diffusion in the network, you have always fraction of nodes which does not have it yet.
That's correct.
Your node use. So as time passes, you have this fraction shrinking, obviously, but you have every single node has this kind of time when he has the chance of receiving something first. Because you don't have the bandwidth to just send it.
That's right. If you could send everything to everybody at the same time, you're done. But remember, I'm normalizing to one message at a time.
Yeah. No, I was just asking about what is it worst case or
Is it worst case or is it what?
or is it more precise than worst case?
It's worse than worst case in a way. You know, it's just I'm pretending that a node is being asleep for a period when it's actually not asleep.
Yeah, but they are asleep from the point of view of that specific.
No, they're not actually asleep. Okay, so there's reality, which is better than this, and this is my analysis, which I'm doing because I'm lazy. Okay, so to me, to do a more thorough analysis, that would take more than the morning. Okay, so this is what we can do together in half an hour. Okay, but that's absolutely not what's happening. Okay, node U is not asleep. Okay, I like to sleep, so that's why I am saying that node U is asleep for until that period of time. Does that make sense? Okay, yeah. Okay, so you look at this, and you know, forget about the 1 over q. This is basically 1 minus 1 over n to the n. You know, it's roughly 1 over square root of e. It doesn't matter what it is; it's a number. Okay, so now I have a Bernoulli process. And the probability of failure is 1 over square root of e. How much time until I get a success? It's 1 over 1 minus the probability of failure. Okay? So, you know, if my probability of failure is 10% is 90%, then it's going to take me 10 times to get to something. If it's 1/2, it's going to take me 2 times to get to success on average. Make sense? Average. Great. So the mean time spent in phase I, well, remember, phase I is the time until node U bumps up its yeah?
Why is the probability that a helpful node increases the dimension 1 by n?
So because, you know, it's which of the nodes is going to actually talk to you. That's right. So, sorry, the question was why the 1 over n? Yeah. So, now, what is the mean time spent in phase I? Okay, it's this time here, the Ri, which was the time until I got to 1/2 of helpful nodes, plus the time that once I got to 1/2 of helpful nodes, I actually increased my dimension. It's the sum of the Ri plus this. So what's the time until U gets to K? Well, it's the sum of this, which is all of the Ri's. Okay? The times when it was sleeping. It wasn't actually sleeping, but in our pretense it's sleeping. Plus, after it wakes up and half of the nodes are helpful, how much time it was spending, and there's K of these, right? Because there's K rounds. That's the time until you get to K, and you complete your matrix, you shout bingo, and you decode. Yes? Okay. So this, because it was a constant multiplied by K, this is obviously order K. This is you adding K of them, but you know, when you look at what's happening here, it's log K over K. This is basically like a constant. This whole thing is also order K. Okay? You see? Right? Because think of the I as being just a fraction of K, right? So you start at I being, you know, 10% of K, 20% of K, et cetera, et cetera. Okay? So this is also order K. So the whole thing is order K. And I cannot do better than order K because I have K messages. Ta-da! Oh, come on, that's cool. Right? Order K. Right? Even if you sleep half the time, order K. All right. So, basically, this is why you get to this optimum. And what does this do for you? Well, here's some pictures from the testnet. And here you have optimum P2P versus gossip sub. We have about 100 nodes all throughout the world. I think this was done with about 60 nodes. I forget, but I could be wrong, but maybe it was 50. So what you see here is your message size here is 6 megabytes, one message per second, and you can see the delay and the standard deviation. Okay, so much smaller delay and much smaller standard deviation. Here you see when you start bumping up the message size, in this case 10 megabytes, here you start going unstable, basically. Here you're still very small, okay, with very small. So here you're already at something crazy like, 30 seconds, and here you're still at like 1.5, under 1.5 seconds. At some point also, you can break it. So you can go to a smaller message size, say just 4 megabytes, but just bump up the rate, 5 messages per second. And this is not that you have a zero delay, it's because you've basically completely clogged up the system. Yes?
So here you are comparing to the actual
Correct. Correct. So this is the, yeah, that's.
So you're segmenting in the LMC and you're segmenting in the
Yes, but it's not, yeah, so there's some, yeah. That's correct. That's correct. But it's not very tight segmentation. So it's not just because you're doing it, yeah. But that's a good point. Great point, absolutely. Basically, I showed you some snapshots. Here's some data. Here's the latency versus the message size. Here, the latency versus the message size. And here's the average. And here's the standard deviation. Okay? Now, what you can see is this is highly nonlinear. And I'm just going to quickly remind people why this is nonlinear. So, basic queuing theory. On the abscissa, we have the utilization factor of a system, which goes obviously between 0 and 1, 1 being 100%. In queuing parlance, this is usually denoted lovingly as rho. On the ordinate, we have delay. Usually I'm always like saying people, sorry for my cursive, but I'm in France, so I'm just going to go cursive and just to heck with it. Okay, what is the relation from one to the other? Obviously, my delay when I have nothing going on is 0, right, unless something went wrong. And then, as I get to higher and higher utilization, the delay goes massively nonlinearly. The formula is rho over 1 minus rho. When rho is getting close to 0, this goes to infinity. So you're seeing that nonlinearity show up here. Now, it's not that we wouldn't have a nonlinearity at some point with us. Of course we would. But what we're doing is we're basically changing, we're renormalizing the rho so that our 1 is somewhere over here. So ours is going to look like this, right? So here, when you're already going nonlinear, we're still in the flat part. Does that make sense? Okay. So basically, that's what we're seeing here. We also see a decrease in the second moment, in the square root of the second moment, the standard deviation. Just another very quick note about queuing. Variance is not just annoying, right? That you don't have a very steady type of service. Variance in one part of the system actually transforms over the entire system into higher delay. Okay? So actually the overall delay is proportional. It doesn't just go with this. It's also proportional to the square of that, the square of the standard deviation. So having a modification in standard deviation, you have to square that to actually see what the effect is over the entire system. Okay? This is called the Polacek-Hinchen formula, usually shortened to, affectionately known as PK. So that's the PK formula. So the standard deviation really, really matters. Okay? So this is why you get such huge gains. Right? So it's optimum, but it's not just, okay, it's optimum and it's 10% better. It's optimum, it's a heck of a lot better. Okay. I'm not going to go into how people use algebraic coding in other aspects, in other systems. Suffice it to say that if you use a structured code like a Reed-Solomon code or a Raptor code or a Bose-Chaudhuri-Hockenheim code or a code that you picked out of Lynn and Costello, you will have much, it won't scale. So you basically will end up with roughly the same behavior as no coding. Okay? Shameless plug. If you have trouble sleeping and, this jet lag is getting to you, what better way to go to sleep than reading network coding for engineers? Yes, this thrilling tome is finally out. And you can entertain yourself and look more into the details. We don't cover gossip in here, okay? But definitely all of this matrix stuff and finite fields and what have you, that's going to be covered in great detail, and you can play with it. It's in memory of my main collaborator with whom I developed algebraic network coding, the late, great Ralph Kurter and his wife. Okay, so connect with us. Read our papers if you want more thrilling high-level equations. Thank you for all the fantastic questions. I'll be here during the entire workshop, and I look forward to having more discussions. Thank you. Are there any other questions? I know we had some as we went along. Yes.
You mentioned, I understand why reciprocal or other stated code doesn't work, but why something like a replica code also doesn't work?
Yeah. So it doesn't work because it's a centralized end-to-end code. Okay. So look at a node, a four-node system, three-link system, where say you have 10% losses at each time. So what's the difference between a Reed-Solomon and a Raptor? In a Reed-Solomon, you have to tell me ahead of time exactly how many losses they're going to be, roughly, right? You have to give me a bound. A Raptor code is called a rateless code, which just means I don't know. I'm going to keep sending until it's done. So think that I'm growing this matrix with time. But it's still structured. It's still binary. Remember what we talked about binary, don't do binary, right? So with a Raptor code or a Reed-Solomon code, basically, if I'm going to have 10% losses on each of these, the throughput is going to be the throughput that corresponds to having something get through the first and the second and the third. Okay? So roughly, if I have a probability of loss P on any of these links, so if P is my probability of loss, 1 minus P is my probability of getting through. I have to get through all of them, so I have to multiply the probabilities of getting through. These are independent. 1 minus p to the n. The throughput with a Raptor code goes down exponentially with the size of the network. Let me repeat that. Exponentially, it dies. It just dies. So, question is, what happens if instead you encode and decode at each link? Okay? So, good question. So, first of all, sometimes you can't, because the intermediate links, if you have a daisy chain, you might encode and decode, encode and decode. If you don't have a daisy chain, the intermediate nodes cannot even decode. Right? This guy, you want him to decode. This guy, is the source. But these two, why do they need everything? But, and I didn't pay you to ask that question, correct? No, I didn't know you before this. Okay, good, because this is exactly what I had skipped. Let me look at something like this, which is, a hierarchical system, like you would see in turbine/rotor in Solana, or like you would see in Medard with RaptorCast, right, which is a kind of basically fountain code. All right, I'm just going to step you through what would happen if you decode at each one, which is what you would need to do so that your throughput doesn't go down exponentially. Your throughput may not go down, but what about your delay? Suppose that everybody needs to receive. I'm just going to step you here. Basically, this shows when RS is complete in yellow, RLNC is complete, and fountain codes are complete. I'm not going to walk you through the whole thing, just to say, in this example, RS is not done, fountain code is not done, we're done after slot 8. Everybody, after slot 4, all 8 nodes got everything. So, this is an example, right? So, yes, a rateless code like a fountain code will be better than an RS. You can see it here. You've got 7 out of 8 at time slot 5 rather than 6 out of 8. But that's not going to get you out of the woods. It's not just suboptimal. It's like the difference between 1 and 0. Right? So for us, no matter how large the n, the throughput stays at 1 minus p. Okay? Okay.
What we do with the two-dimensional lead
Yeah, no.
that we do have to look at. I know it's not optimal.
But it's not that it's not just optimal, right? It's
So then we do have the
yeah.
which does
No, I'm sorry. You read some. It's so far off. It's so far off. Just some things you just can't save. You can't save a read some. It's not. It wasn't developed for this at all. Yeah, no. And look, I'm a code. I misspent a lot of my youth on these Reed Solomons. I'm not. Yeah. I think he had a question, so let me just, yeah. And actually, let me suggest the following. Why don't we all go coffee and you can pepper me with questions. Thank you all. You were so interactive, so engaged. Thank you.
Thank you, Muriel.